So a phasor diagram is just a visual representation of this equation, and then from this equation we need to put into the phasor diagram, which is a illustration. So the first thing we need to draw Vs. Vs usually at the 0 position. Remember, it is a this is a vector. Vector. It must have a magnitude and also angle. So Vs is usually at 0 degree, the first one. And then the second one, we need to know where is the Is. Either it's a lagging, unity, or leading. So now this is a lagging power factor. Assume it's a lagging power factor. So my Is direction is here with a theta like this one. Then I need to times R equivalent, which is the third one. I need to find this component. So I know that this one is just a magnitude. So the vector of this one will be this. This line will be parallel with this one. Okay, must be parallel. If let's say the I is like this, it must be like this. Okay, so now it's in this way. So Is R equivalent will be in this way, and then we know that Is X equivalent is 90 degree from here. So we will have a 90 degree then going up. Okay, then this is the fourth one. The fifth one is the last one, the resultant. Okay, this is the phasor diagram. Next, if it is a unity power factor, first I need to draw Vs. Second, I need to know where is my Is. Third, my Is R equivalent is same direction as Is. Then 90 degree Is for Is X equivalent because of the J, and then I draw the resultant, which is Vp divided by A. So this is the equation. Just now this one is a unity power factor. What if a leading power factor? So first my Vs. Second, where is my Is? Third, parallel. R equivalent Is is parallel. Okay, parallel. And then it must be 90 degree. And then we will go to the end as my resultant. Please bear in mind, all of the vectors are continuous. For example, from this point to this point, okay, then I start from this point to this point, then I start from this point to this point, so that which is referring to the right hand side. Then this is my resultant. Okay. So as a conclusion, a brief summary, the VR of a transfer of the various power factors like this. If lagging power factor, leading, unity power factor. Oh, this is unity. Sorry. This is unity. Okay. Where is lagging? Oh, this is lagging. This is unity. Sorry. This is sorry. This is a leading. Leading. This is unity. This is lagging. Okay. This is just a typical one. So next we want to calculate the transformer efficiency. Transformer equivalent circuit can make efficiency calculation easily. For example, this one, because we know there are three types of losses. One is copper loss, one is eddy current loss, one is hysteresis loss. Usually we combine the eddy current loss and hysteresis loss together as one. So we come to one is a copper loss, one is a core loss. So copper loss from a primary side is come from here. From a secondary side is come from here. This is a copper loss. For the core loss, for primary side is come from here. For secondary side is come from here. Okay. So next, we need to know what is a formula we need to use first. So efficiency is P out divided by P in. Then my P out is P out lah. P input is actually my output plus loss lah. Okay. Then my P out is actually VI times cos theta. So my P loss actually is come from P copper plus P core. This is my P loss. P copper plus P core. Okay. So This is how we want to find our efficiency. So P copper is come from I square R, or V square. For core loss is V square over R, because we have, okay, I square R, because we have the I for this one. For the core loss we have the V from the node here. Same as well for the copper loss, we have a I here. Then for the core loss we have a voltage here. That's why we use V square over R. Okay. The example. So now rating, and then I have a testing. I need to find those few things. So let's have a try. Connection for transformer, open circuit, and then not so important. First, we need to find the equivalent circuit refer to the high voltage side. So first we need to find the transfer ratio. Then the theta open circuit is 84 degree. Given. Then I want to find this one, right? So remember, with a negative 84 degree. Given. Then I convert into this value first. I get polar, and then I convert into rectangular form. Then I find my RCS and XMS. Why it is S? Because it is secondary side. High voltage. You see, this one is given on the low voltage side, right? Low voltage is on the secondary side. So this is secondary. And then because we want to refer to the high voltage side, which is a primary, so we use conversion, refer to primary side. And then we find this value. Same, short circuit, it is done as a high voltage side, which is a primary side. Okay, so find the angle. Then I want to find this polar form. So given, I can find my degree. I can get my degree. Then this one is given. Then I put into the polar form, rectangular form, compare to get this one. Then I find my R equivalent and X equivalent, which is done at the primary side. Refer to primary side. First, I need to this V primary vector, I primary vector second. Third, V secondary referring to the primary side, which is equal to A times V secondary vector. And then fourth, I secondary refer to the primary side with a vector. Fourth one. Fifth, we need to write RCP because it is in primary side. Next, JXMP. Next, R equivalent P. Next, JX equivalent P. This is how we refer the primary side. So we also need to refer to the low voltage side, which is a secondary side. Next, we just directly convert the primary side to secondary side, or we just directly same as well, do conversion. Then we write again A. Okay, we convert the primary current to secondary side, become this one. We convert primary voltage to secondary side. We convert primary current to secondary side. Third, we write VS. Fourth, we write IS. Fifth, we write RCS because refer to the secondary side. And JXMS, and then R equivalent S and JX equivalent S. So how to find the voltage regulation? Okay, usually the no load is come from here. Full load is come from here. That's why we need to find the phasor diagram. Okay, and also it must always refer to the secondary side. So what we need to do is we convert to, we need to find the S rated, and then some more, because we know that the output is 230 volt. This one is fixed, you know. You see, this one is 230, and then start from, it is always start from 0 degree. Okay, for this equation. This one is calculated. This one also, this one is from IS lah. Lagging is given here. Okay, lagging power factor. This one is calculated, and then this one from here. Then we want to pop up, then we get this one. So in order to find the voltage regulation, we use this one minus this one, divide by this one, times 100%. Then we get 2.1%. Okay? So this is how we need to know what is a phasor diagram, where from this equation we can see that if from this equation, okay, from this equation we can see that if now the transformer is connected as a 230 volt, what if at that instant time I take off the load? At that time actually the voltage is 2.34.85 at that instant, but after that it becomes 0, right? It will become 0 because there's no connection, right? It becomes 0. No, it won't. Sorry, it won't become 0. Sorry, it won't become 0. It will just become 234.85. So this is the voltage regulation. How good is that? So the regulation is about 2.1%. So what if at a power factor at 1? So we need to change this this one. So the regulation is 1.28%. If 0.8 leading, so the current is changing, then the voltage regulation become negative value. So this is how, when we talk about voltage regulation, we must always remember phasor diagram, and it is always in secondary side. When we draw out, yes, it becomes like this lah. So first we need to draw the Vs, then parallel with the Is, we need to know where is the direction of Is. It is negative value. So you see the direction is the same. Then 90 degree, go up, then go to this side. Same as well for the rest. So when we plot for many loads, then it becomes this line. So what is the efficiency? So if 0.8 power factor lagging, so efficiency is P out over P out plus P loss. So we need to find the P loss. P copper loss, P core loss. I square R, V square over R. Okay, from this circuit, this is my R. From this circuit, this is my core. Right? So I need to know this one. I also need to know this one. So my IS is at 65.2. Then my R equivalent is this one. My VPA is this one. Calculated from phasor diagram. This is my RC. So I get my this one. Efficiency, use this one. So V secondary times I secondary cos theta. Cos is given a power factor. P core calculated, P loss calculated. Then I have my efficiency. So that's why we need to know the equivalent circuit. Yeah, the last part is the auto transformer. So we'll talk about the voltage current relationship in an auto transformer, apparent power rating, weightage, advantage of auto transformer. Okay, sometimes we need to increase the voltage from 110 to 120 volt, or from 13.2 volt to 13.8 kilovolt. Sorry, 13.2 kilovolt to 13.8 kilovolt. It is very wasteful and excessively expensive, very expensive to wind a transformer with 2 full windings. Each rated is about the same. Rated means the power ratings is almost the same, and or the voltage almost the same. So a special purpose we call transformer, called as auto transformer, can be used to do like this. So have a look on the conventional transformer and the auto transformer. This one is step up one. Conventional, we have a VP, IP, VS, IS, and then one winding, second winding. Okay. Now, if let's say we put into the auto transformer, we move this winding to the top, become like this. So you see, this one is common one. Is still at the bottom. This one is N series. We put at the top with one connection. Okay, note are still the same. At top, at top, at top, and top. You see, note, dot. Sorry, dot. So this is the circuit. First winding we call it as a common winding, VC, NC, because voltage appear on both sides, or on this side and this side. Fourth, second winding we call as a series winding, because it is connected series with a common connected through like this, we call it a series winding. So this is the difference between auto transformer and conventional. Conventional transformer, there's no connection. Auto transformer is connected. Okay. So because the transformer coil are physically connected, and new terminology has been used. For example, VC used as a common voltage. VC, we use common voltage. Common current, IC, this one. Series voltage, series current, series voltage, series current. Voltage at the low side, okay, low side. Voltage current at the low side, voltage at the high side, current at the high side, high voltage side. So this is a step up auto transformer, voltage low here, high here. This is step down transformer from high to low. Okay, so how we draw the transformer? First of all, this one. Second, the dot. Okay, maybe I put laser pointer here. The dot. Third, plus minus V low. Then current I low. Then plus minus VH. Then current IH. Then plus minus V common. Then where is the current of the common? Plus minus V series. Then the current series. Then that's it. Okay. So voltage and current in the coil, these are the equation that we need to use. VC divided by voltage core divided by VSC, actually NC divided by NSE, and then NC times IC equals to NSE times ISE, VL equals to VC, VH equals to VC plus VSE, IL in, then out become IL equals to IC plus ISE, IH equals to ISE. Or just from the circuit lah. Then yeah, we want to study the voltage and current relationship in an auto transformer. So first of all, just now we have a VH equals to VC plus VSE, right? It happens, actually this one happened for step up or step down auto transformer, but here I only display the step up auto transformer. So VH equals to VC plus VSE. No, this one is a step up auto transformer, this one is a step down. So VH is a VC plus VSE. Same as well. VH equals to VC plus VSE. Then VC over VSE equals to NC plus NSE. Now I change this one VSE by using this equation. Have this one. Then VL equals to VC, right? VL equals to VC. VL equals to VC. So I change the VC become VL. Then I factorize VL. I have this equation where VL divided by VH actually is a NC common divided by these two. Summation of these two. Or my VL divided by VH actually is my this core divided by summation of this winding. So this is the voltage relationship between V low and V high. So the current relationship for I low and I high. So first of all, IH, you see for the step up transformer, I low go in, come out is I core and ISE. So same as well. I low come out is actually come from IH plus ISE. Then with the NC, IC, NSE, ISE, I can substitute IC become like this one. Then I substitute ISE with IH, I have this one. And then I found the relationship between IL divided by 8 IH actually is a summation of the winding divided by core winding. So remember these two equations, yeah? Next, noted that all the power traveling, okay, from one of the auto transformer, first of all we need to know what okay, noted that not all the power transfer from the primary to secondary in the auto transformer goes through the winding. What is that mean is for example SE input is VL times IL, output is a VH times IH. So my SIO is an input output apparent power transformer. Actually is SIN equals to SOut equals to SIO. And apparent power in the transformer winding means the transformer winding rating is actually VC times IC and VSE times ISE. So now I know that my SW, which is the winding apparent power, either this one or this one. Actually, it's a VC times IC, right? Then I substitute my IC with this one. I have this one. Then I use this equation. I become this one. Okay, I substitute this equation into here. I have this one. Then I found that the winding and input-output apparent power is related with this ratio. So therefore, the ratio of the apparent power in the primary and secondary of the auto transformer to the apparent power actually traveling through its winding. Okay, which means the power from how to say the ratio of the apparent power in to the apparent power traveling through its winding. Therefore, the ratio of the apparent power in the primary and secondary of the auto transformer to the apparent power actually traveling through its winding. I think this statement saying that the power traveling through the winding is related to this ratio actually, which has come to here S input output divided by S winding equals to NSE plus NC divided by NSE. So this equation demonstrates the apparent power rating advantage of an auto transformer over a conventional transformer. Which means we'll see this one. Okay. For S input output is apparent power entering the power and leaving the secondary transformer, which is go in and go out we call S input output. SW is the apparent power actually traveling through the transformer winding. This one. The rest passing through the primary to secondary without being coupled through the transformer winding. Okay, for example, if let's say I have S in, S out is maybe 10 VA, 100 VA 100 VA. But the SW maybe 80 VA, which means when the 100 VA going into this one auto transformer, only 80 VA, will be used here. And then 20 VA is directly go to the output. Noted that the smaller the series winding, the greater the advantage. We'll see through this example. This is example. For example, a 5. Let me put in the pen first. A 5000 kVA auto transformer, conventional one, which is like this. Here, this one. Conventional, it has a 5000, and then conventional has a 5000 kVA. It connects auto transformer connecting a 110 kilo system to a 138 kV, which 110 kV to 138 kV, which is a step-up auto transformer, would have a NC and NSE turns of a 110 to 20, so 110 to 28. Such as an auto transformer would actually have a winding rated as this one. So I use the formula, I find this one. So we can see that actually the winding rating is only 1015 kVA. But the traveling from 5000 kVA from input to output, okay, which means it can send the power as a 5000 kVA from the input side to the output side. Okay, so for example, this is 1000 kVA, which means the winding only need 1000 kVA. However, another 4000 kVA is directly passing through from input to the output. So the auto transformer could have a 5 times smaller. Which means if let's say I use this conventional, connect at this one, it become like this, whereby this is a 5000 kVA, this is a 5000 kVA. Okay, but if I don't want to do the reconnection, instead I want to redesign. Okay, instead I just want to redesign. I just need to design the spec where the transformer winding only need 1015 kVA. So which means 5 times smaller. I don't need to put so much money to build as same as the conventional with the 5000 kVA of the transformer to do as an auto transformer. So which reflect this statement. The auto transformer could be 5 times smaller than the conventional transformer, and it is much cheaper because cheaper cost, right? Cheaper material. For this reason, it is very advantageous to build transformer between two nearly equal voltages as auto transformer. Or I can put in this way: if I want to design 110 to 138 kVA conventional one, I may need 5000 kVA winding on both sides. If I design in auto transformer, I just need two windings with about 1000 kVA, but the performance still the same, which deliver 5000 kVA from the low voltage side to the high voltage side. So this is a sample question. For example, dotted side is H1, H1, H2, X1, X2, dot, because I1 is flow in, I2 is flow out, then VP, VS, 600 volt. Okay, how can we reconnect these things into a auto transformer? For example, this is step down transformer. We need 720 to 120. First, we need to know what is this. It is a step down transformer. This is step up, right? So first we see the step down transformer, auto transformer first. Second, we need to find the common one. The common is 120. So I need to know 120, 120. So 120, the third one. Fourth, we put another one as the top, 600. And then we compute as make sure it is 720. Okay? So it becomes 720, transform into 120. So what if we want to reconnect into 600 to 720? First, we need to know it is a step-up transformer. Second, what is the common one? Common is a 600. Because I need higher here, I must have a 600. And then my input is a 600. So the common one is a 600. Third, this one. Fourth, the series, which is the left. The rest one is a 120. Next, my 100, 720. So this is how we do the reconnection. So you can let's have a look. What is this? The rating of the 100 VA, and this is the transformer connected to form a step-up auto transformer. So this is a conventional one. Then we want to connect as an auto transformer, which is step-up. So I need to draw like this. Step up. We need to find what is secondary voltage, maximum volt ampere rating, rating advantage. Next. So we use a formula. We found that okay, my high voltage side is 132. Then I use the equation to find what is the ampere rating. So my S in, S out, use the equation, which is a 110 VA. 110. It can cope with the 1010 VA. Then so it can do as 11 times, where I use a conventional one, but I can deliver 1010 VA for this step-up auto transformer, or 11 times. Okay, so put it in the equivalent circuit. We can see that the winding rating only 100 VA, but we can deliver 1010 VA from input to the output, which is 11 times. So you can see the advantage of the auto transformer. Disadvantage is like this. When one side is short circuit, everything will gone. So it is not normally possible to just reconnect an ordinary transformer as an auto transformer because the insulation on the low voltage side of the ordinary transformer may not be strong enough to withstand the full voltage side. In a transformer built specifically as an auto transformer, the insulation on the smaller coil series is made just as strong as the insulation on the largest coil. Disadvantage of the transformer: there is a direct physical connection between the primary and secondary circuits, so the electrical isolation has no more of the two sides is lost. So thank you very much.